Right, so conics. So in extension 1, as I say, we've looked in detail with the parabola, looking at its parametrics and things like that. That is one type of conic, and that's the conic, as I say, that extension 1 looks at. Extension 2, we take a little bit further. We'll also look at the ellipse and the hyperbola, and we'll do similar things. You know, find the equations of tangents and normals, look at some geometric properties, and you'll be surprised how many are, if not just similar, are actually the same as with the parabola. This hopefully sounds familiar. Right? The locus, however you say that word, of points whose distance from a fixed point, which we call the focus, is a multiple, which we call eccentricity, and we label it E, of its distance from a fixed line directrix. Now, that's very similar to our definition of a parabola, if you remember. The difference is I've got is a multiple of its distance, whereas in a parabola, you'll hopefully remember it was is equal to. So in other words, the eccentricity of a parabola is 1. Is 1. So it'll be the same as its distance to the fixed line. So here's a cone. Now, I didn't have room, but I really should have drawn a double cone. And by a double cone, I mean imagine another cone, same size, sitting on top, the 2 points on top of each other. If I take a slice anywhere horizontally, I will get a circle. A circle, there it is, it has an eccentricity of 0, and it's the first of the conics. So what actually is this eccentricity? And what it is this. The cone, the slant edge, will have a particular slope. Different cones will have different slopes, obviously. But if you imagine that the slope is, we'll just call it M for slope. See, that's what we usually call it. Okay. If I was to slice with a slope of some multiple of M, that multiple being the eccentricity, we will get different shapes. So if that multiple is 0, so slope is 0, it's horizontal, I get a circle. Okay. So that's another relationship between eccentricity, not only in this definition, but with regards to the cone itself. It's a multiple of the slope of the slant edge. If I now, here we go, let's draw in that one. There's the ellipse. In order to cut through and get an ellipse, the slope must be smaller or shallower than the slope of the cone. Because I need it to cut through both sides of the cone. Now, there's a dodgy picture of it, which basically means its eccentricity is 1, or the multiple of the slope is between 0 and 1, if you like. Now, that's a really bad diagram, but in order to fit it in, I sort of had to draw it dodgily. That's meant to be parallel to the slant edge. Obviously, it's not even close to being parallel. Use your imagination. Okay? Because the parabola, as we say, is when eccentricity is 1. So in other words, if I get my slice so that it's parallel, so it has the same slope as the slant edge, then we will get an ellipse. Now, each one of these 3 that I've just done will only go through one of the 2 cones. But as soon as I get the multiple of that slope to be greater than 1, it will end up cutting through both cones. And that's when we get the hyperbola, or the 2 branches of the hyperbola. Because one branch will be in the lower cone, one branch in the other. Now, I've drawn the maximum one that's possible there where it's vertical, so it has an infinite slope, but it would, if you imagine the cone above, cut through above as well, you'd end up with the 2 branches. So when the slope is parallel, that's the parabola, because that's the first time that it'll go through the base. Okay. But then when it's bigger than 1, it'll still go through the base, but we no longer have the parabola. They will now become different hyperbolas, depending on what the eccentricity was. And so that's how the different shapes were created using the cone. And as I say, we also ended up later on, well, not me, I wasn't involved, the Greeks many, many years ago also discovered that, hey, that multiple of the slope turned out to be the same as this multiple of its distance from the focus to the directrix. So let's have a look at our ellipse. It's the first of the shapes we want to have a look at. So the eccentricity is less than 1. And here's our standard one, centered at 0, 0. And just like when we looked at the parabolas and all the parametric stuff we did, its vertex was at 0, 0. Same with ellipse. The center is going to be at 0, 0 for all the parametric stuff. Yeah?
Does that mean for all questions that it will be that standard ellipse, or would it be moved around?
I think I just said for the parametrics questions, they're all. All would mean all of them. Okay. There's my focus, which you'll remember we label S. And there's my directrix, which I've labelled Z in this case. Now, our definition was any point on the ellipse is equal to a multiple, or its distance to that point to the focus is equal to a multiple of its distance to the directrix. So I've put A right on the vertex here, which is a distance little a from the centre. But we know the distance from S to A will be the eccentricity from A to Z. The difference is with an ellipse is it's a closed shape. So right on the other end, there's this other point, the other vertex, A dash, but it would still obey the same rule. So the distance from S to A dash will equal the eccentricity times its distance from A dash to the directrix. So if I play around with those, SA dash plus SA then must equal 2A. Because if you have a look, SA goes to one vertex, SA dash goes to another vertex. So together, no matter where that focus is, I would get the, for want of a better word, diameter of the ellipse. If I was to go SA dash minus SA, well, SA dash we said was eccentricity times A dash Z minus eccentricity times AZ. What I've done there, I'll play around with this a bit more before I say that. Well, A dash Z minus AZ would also be the distance from A dash to A, which is 2A. So we've got eccentricity times 2A. But what I've now done is I've created some simultaneous equations here that I might be able to play with. So there's our diagram. So if I add them together, two lots of SA dash will be 2A 1 plus E. And if I subtract them, then I get two lots of SA is 2A1 minus E. All right, we're now going to come up with some coordinates for the focus, and something amazing now happens. The distance from the centre to the focus would be the distance from O to A minus the distance from S to A. Well, distance from O to A is little a, and we've just said the distance from S to A is A outside of 1 minus E. So in fact, the coordinate for the focus just simply turns out to be A times E. And that is the same as a parabola, because remember, it was 0A, but of course in a parabola, the eccentricity is equal to 1. So it is AE. So same feature as a parabola. The difference is with an ellipse, you actually have two foci. It's a symmetric shape, so whilst there is one here at S, over on the other side, there would be one at S dash as well, we would call it. And it'll be the other focus. All right, let's find the equation of our directrix. Well, the distance from O to Z would be OA plus AZ. So it's going to be OA plus SA on E. If I just play around with AZ, remember our definition I've used there, rearranged it to get that AZ would be SA over E. Right? Subbing into that one, and I get another very simple equation, A over E. So the focus is A times the eccentricity. The directrix is A divided by the eccentricity. And there are also two directrices. Each focus has a corresponding directrix. So you'd pair up. So the other one would be minus A divided by E. Okay. So we now know the focus has coordinates AE0. I'm going to pick any point on the ellipse. We want to come up with the actual equation of the ellipse here. P is the point xy. It's a random point. Its distance to the directrix we'll be interested in. So I want to find out the coordinates of n. It's going to have an x value of the directrix, which we just worked out was A divided by E. And it must have the same y value as our point P. So I'll just call it y. And we said SP, distance from P to the focus, is eccentricity times the distance to the normal. So using my distance formula then, I can sub in squaring both sides. And then I want to expand that all out, tidy up some terms. I've grouped them together in an interesting way. I've just got the x squareds together, the y squareds together, and then the number itself, similar to what we would do with a circle. Going to divide everything by a squared 1 minus e squared. And we get this x squared on a squared plus y squared on a squared 1 minus e squared is equal to 1. That's still a little bit messy. We can make that even neater. Because we know that the y-intercepts, we've just called them b, the y-intercepts. So if I sub that in, x equals 0, y equals b, I get b squared on a squared 1 minus e squared is 1. So b squared is in fact a squared 1 minus e squared, which makes the formula a lot neater. Now, that's how we end up getting it for an ellipse where a is greater than b. The general equation, x squared on a squared plus y squared on b squared is equal to 1. Now, if it was a circle rather than an ellipse, then a and b would be the same amount. Okay. And a squared would turn out to be the radius squared because you'd multiply through and you get your x squared plus y squared is equal to the radius squared. Where b squared is equal to a squared 1 minus e squared. The focus will be plus or minus AE0. The directrices plus or minus A over E. E is that wonderful thing we call the eccentricity. Now, if you have to find the eccentricity, we usually play around with this b squared equals a squared. But if you make e squared the subject, it's usually easier to find it. So e squared actually turns out to be a squared minus b squared over a squared. That's quite simple. And you think, well, hang on, what happens if I get the b and the a the wrong way around? Remember, this is for an ellipse where a is bigger than b. So if you get it the wrong way around, you'll end up with a negative number, and you'd have e squared as a negative number, so you know I've got it the wrong way around. So it's a squared minus b squared on a squared. Now, we don't use the word radius or diameter with an ellipse. We use the term major semi-axis and minor semi-axis. So they, if you like, are the two radii of the ellipse. See, in a circle, it doesn't matter where you draw the radius, it's always the same amount. So we can have one word for all of them. When we're defining an ellipse, we talk about the smallest one, which is the minor semi-axis, and then the largest one, which is the major semi-axis. Semi-axis, because we're talking about half of it, the equivalent to diameter then would just be major axis, minor axis. Now, what happens if B is greater than A? All it means is your ellipse now, instead of being elongated along the x-axis, it's now elongated along the y-axis. And so the foci will be on the y-axis instead of the x-axis. Your directrices will be parallel to the x-axis instead of the y-axis. So everything swaps over, if you like. So foci is on the y-axis. It will now be a squared is b squared 1 minus e squared. Okay? So the a and the b have swapped round because we've swapped axes. The focus now will be plus or minus BE in the y value instead of AE in the x value. And the directrices will be y equals, instead of x equals, plus or minus b divided by e instead of a divided by e. And again, if you think of eccentricity this way, you can't go wrong, because if b squared is bigger than a squared, then you'd go, oh, hang on, it's negative. It must be the other way around. You can still work out your eccentricity. Just throw this in here. You may or may not be aware of it. The area of a circle is actually the area of an ellipse formula. It's just that in a circle, the major semi-axis and the minor semi-axis are the same thing. So it's pi r pi r squared. So an ellipse, it is simply pi ab, the major semi-axis multiplied by the minor semi-axis. All right, we're going to find all the very basic conics questions are like this, where we just go, okay, show me you can find all the important features. They may or may not ask you to draw the sketch. So x squared, this is a standard one. A squared's bigger, so it's along my x-axis. So A is 3. Well, A and B are always positive amounts. So I'm going to work out my eccentricity using the a squared minus b squared over a squared formula. And it turns out to be 4/9, which is what we're expecting, because for an ellipse it should be less than 1. So eccentricity is 2/3. Foci then, 3 times 2/3, well that's 2. So plus or minus 2, 0. Directrices, A divided by E, 3 divided by, invert, multiply, we get plus or minus 9 on 2. To draw it, I'm going to use a method here called the auxiliary circle method. Okay. So what I've drawn in is the auxiliary circle, which is the circle which has the same radius as the major semi-axis. Now this ratio of B on A, which for our question, which is √5/3, comes in very handy if we want to plot a very accurate ellipse. This is how we do it. We can draw any vertical line. Well, the y-axis is already drawn for me, so that's a convenient one to draw. I get my ruler and I measure from the center to the circumference of my auxiliary circle, and then I multiply that measurement by B on A, √5/3, and that's where I plot my point. So, because I know the radius is 3 units, that obviously will become √5, which is what we know what B is. Okay? So that was the easy one, of course. We knew that was going to be √5. But I can do the same thing on any vertical line. If I draw a vertical line, measure from the axis to the circle, multiply that measurement by √5/3, and that's where I'll plot my point. The wonderful thing, of course, it's symmetric, so whatever I did above, I'll do below, but then I can also do on the left-hand side as well, because you've got symmetry that way as well. So I'll get a few more points. And basically, you can draw in as many vertical lines as you like, depending on how accurate you want your ellipse to be. So there's another one. By symmetry, I can draw them on the left-hand side. And another one, you can see the ellipse is starting to take shape. There it is. Now, ooh, and then we draw in our ellipse going through all those points. So there's my lovely ellipse. I don't think I've ever seen them ask you to do it via the auxiliary circle method. I'm just saying this is a nice way if you want to draw an accurate graph. Usually for the sort of questions we're going to get, just get your template, draw an ellipse, label in the points, it'll be fine. In fact, the only time I've ever seen them asked with the auxiliary circle was actually in the general maths exam, rather than... It's the one thing they have in common in the general maths as they do in extension 2 maths, but they don't do it in extension 1 and they don't do it in 2, is how to draw an ellipse using this auxiliary circle method. Oh, thank you for that. Oh, something else wrong. Okay. So, plot the focus. There it is, 2, 0. The other focus over here at minus 2, 0. Draw in the directrices, and there's our diagram. Major axis is 6 units. Remember, be careful, read the question. Is it asking for semi or is it asking for the whole thing? So major axis would be the whole diameter, for want of a better word, 6 units. The minor one is 2√5. Okay, here's one where the centre has been shifted. Okay, whilst I say, they're not going to ask you ones like this, it would be very unusual. There's no reason why we can't handle it using our shifting idea, same as we've done for every other shape that we've seen. So I will need to complete the square on this. I'm going to divide everything then by 36. Because remember, when we complete the square, we like the coefficient to be 1. So if I divide by 36, on the top of the fractions, my coefficient of x squared and y squared will both end up being 1. So I'm just looking at the top now. X squared plus 2x will become x plus 1 all squared, but that means I've got to add 1 over 4, so a quarter to the other side. Y minus 2 all squared, so I've added 4 over 9. And adding to that the 11 on 36, amazing, that's 1. Incredible, it's in our general form straight away. I don't have to do any more division. If it was a different number, of course, we'd then just divide by that particular number to make it equal to 1. So then we could read off the data. So now I know the centre of this ellipse is negative 1, 2, just using our basic shifting idea, same as we did for circles and so on. So that's where my centre is. B will be 3. Notice it's bigger than A. So I know the foci will be on the vertical axis rather than the horizontal axis. Eccentricity, so I'm going to go b squared minus a squared instead of a squared minus b squared, and it'll be over b squared instead of over a squared. So we get root 5 on 3 for our eccentricity. So the foci then, well, if it was centred at 0, 0, I'd now simply go b times e, which is root 5. But of course we've shifted it. So we've shifted it to the left 1, so it'll be negative 1 for the x value, and up 2, so 2 plus or minus root 5. There's the 2 foci. Directricity, same idea. It would have been b over e plus or minus, but we've shifted everything up 2, so it becomes 2 plus or minus. So it really isn't that big a deal if they did have an ellipse where the centre wasn't at 0, 0. So this basic sort of stuff, that's fine. But as I say, when it comes to finding tangents and normals, things like that, it'll be centred at 0, 0. Okay, 6a.